All right. So for this morning here, guys, we're going to be kind of going back over something we talked about right at the beginning of the unit, which was mechanical energy. Okay, and we said that mechanical energy has to do with either the motion or the position of an object. Okay, then we started, we did, the acceleration in vehicles, d/t, and all of that, and then we came back to this idea of work and energy. Okay, whenever we do work, we're changing the energy of an object. Okay, now all the problems we've dealt with, it's either been I've changed the kinetic or I've changed the potential. It's actually possible to change both at the same time. Okay, because technically the definition for work is a change in mechanical energy. We've simplified it. I mean, it's still true. It's a change in energy, but it's more true to say, okay, that it is a change in mechanical energy. So whenever I do work on something, it is either going to go faster, move further away from the Earth, or both. Okay, everyone follow me there? All right, so we're changing the mechanical energy of an object. All right, that means that the mechanical energy of the object is the sum of the two kinds of energy we've been dealing with. All right, so the total mechanical energy of an object is kinetic plus potential. All right, that's something that we've certainly got to know. Okay, so that is right here. Mechanical energy equals kinetic energy plus potential energy. In other words, it is the total energy of the object. Okay. So the example they have here is that a ball thrown upward in the air has kinetic energy because it's in motion. It also has potential energy because of its position. Okay, so kinetic and potential energy are closely related. Okay, so they are combined, okay, as mechanical energy, or EM. Right. Right, and sorry, we should probably complete that, which is defined as the energy due to the motion and position of the object. Okay, everybody with me there? Right. So at first, the math of this is fairly simple. If I want to calculate the mechanical energy of an object, I add its kinetic energy and its potential energy together. Okay, pretty simple. We have formulas for both. Okay, we know how to calculate potential energy. It's m times g times h. Okay, we know how to calculate kinetic energy. It's 1/2 mv squared. So it's not going to be hard, right, in order to solve problems related to that. Okay, so here's our example that we've got. That 3-kilogram baseball thrown in a straight line through the air. All right, now we've kind of simplified these kind of questions over the last week where we've just said, well, it was moving, so it just had kinetic. But in reality, unless it was actually just rolling along the ground, it actually had potential as well. The difference is that if the height doesn't change, its potential energy also doesn't change. All right, but we might speed it up or slow it down. Okay, so if I want to calculate the total mechanical energy of this baseball, I've got to figure out how much kinetic energy it has and how much potential energy it has, simply by plugging my numbers into the two formulas and adding them together. So it's a pretty simple operation. So in this case, we have our 0.3 kilogram baseball. So if I'm calculating its kinetic energy, I'll go 1/2 times 0.3 times 20 squared. Okay, and then I'm going to add that to its potential. They told me it's 2.5 meters above the surface of the Earth. So mass, 0.3 times g, 9.81 times the height. And then I add those two together, and I get that the total mechanical energy is 67.4 joules. Okay? Everybody pretty clear on that one? Okay, and that's pretty easy stuff. Okay? Now, if we go back to this bow and arrow example here. Assuming that bow is at ground level, when the archer releases the bow and the arrow flies out of it, okay, assuming that the initial height of the arrow is 0, it will only have what kind of energy when it leaves the bow? It'll only have kinetic, because it'll be moving, but it'll be at ground level. Okay? As it moves upwards, what's going to happen to its amount of kinetic energy? As it moves upwards, it's what? It's going to have less. Because if you shoot something straight up in the air, as soon as it would leave the bow, it would be slowing down. Right? Because gravity would be pulling it back. Right? Now, it may be going slower and slower and slower, but it's also getting higher and higher and higher. So while its kinetic energy is decreasing, its potential energy is increasing. Right? Now, here's the most important thing about the law of conservation of energy, which is what we're talking about today, is however much work this person does, let's say they do 400 joules worth of work in drawing back the bow. We know that when the arrow leaves the bow, it's going to have 400 joules of kinetic energy. Okay? Can it ever have more or less total energy than 400 joules in its entire flight? It can't. Okay? As it flies upwards, that 400 joules of kinetic energy will turn into potential. Right? When it reaches its maximum height, and let's just say it's right here, okay? Its maximum height here, it won't be moving because it is slowed down, slowed down, slowed down, and then it kind of instantaneously stops. Okay? So since at that point it has no kinetic, all 400 joules are now potential, right? Okay? It has all potential energy. And now it's going to start to do what? It's going to come back to the Earth. That potential energy will get turned back into kinetic. When it returns to the Earth, it'll have 400 joules of kinetic energy. Okay? The law of conservation of energy says you can't create energy, you can't destroy it. The only way you can gain or lose it is to have work done on you, which means you would gain energy, or do work on something else, which means you would lose energy to that. The energy is always still there. Okay? It can't be created or destroyed, but it can go to other places. It can turn into other forms. Okay? So this 400 joules that we start with as kinetic is the total mechanical energy of the arrow. Would you agree? Right? Because we said down here, mechanical energy is the sum of kinetic and potential. It just so happens that potential at the bottom is 0. Okay. Right about there, let's say exactly halfway to the top, how much kinetic energy do you suppose it has? About 200. And how much potential? About 200. Okay, see where we're going with this? Okay, that's the concept we're working on today and a bit next week. We're always going to have a total of 400 joules because that's the mechanical energy I put into the system by doing work. Okay, the bow and arrow are the system. I did work on the bow did work on the arrow. That 400 joules of energy is always going to be there. Okay. All right. So the illustration here, that's what we've just been talking about. Okay, an important concept in physics that involves mechanical energy. Okay, so this figure B212 is the bow and arrow person here. Okay, when a person pulls back the bowstring, an average force is being exerted through a distance, so work is being done. Okay, the work is then stored in the bow as elastic potential energy. When the string is released, the elastic potential energy is converted to kinetic. As the arrow rises, it turns into potential and so on. That's what we just talked about there. I would say that is a good example to know, okay, because it explains the connection between work energy theorem and the law of conservation of energy. Right? And that's kind of the big concept in this unit, okay, is that those two things go together. Work is a change or a transfer of mechanical energy, okay, and then that has to be conserved. All right, I want you guys to try 8, 9, and 10 here. Okay, you can give the answers to those. Right? Hey, so the answers are on here. You'll know if you did them right or not. Okay, all you're doing is using this formula here. Okay? Now, it might ask you to manipulate it a little bit. It might tell you the total mechanical energy and then ask you to find the kinetic, okay, or something like that, but it's just a matter of, subtracting one over to the other side. Okay? All right, so I'll give you a couple minutes and then we'll go over 8 together. Okay. So the big thing on question number 8 is the mass has to be in kilograms. Okay? If you didn't put the mass in kilograms, you're getting an answer that is way too big. Okay? So we need to find out, okay, the total mechanical energy, okay, in number 8. Okay? And that means the kinetic energy, 1/2 mv squared, plus the potential energy, m times g times h. Right? So for this question, that's going to mean 1/2 times 0.3 times 8 squared, because the speed was 8. Okay, and then we're going to add that to 0.3 kilograms times 9.81 times the height of the clam, which was 30 meters. All right, and when we do that, we should get 97.89 joules. Okay, everybody with me there? Does that make sense? So that's one of those little things we got to remember. I have never done that on a unit exam, just so you're aware. Never put something in grams, okay? Because I think you got enough on your plate to remember, okay? When it comes to an exam, that a little dirty trick like that's not necessary. However, on a quiz, I would be totally inclined for a small dirty trick like that, okay? All right, give number 9 a try. Number 9 is asking you to calculate the gravitational potential energy using this same formula here. Okay, or rather using maybe a simplification of it. Okay, so let's just say it starts out like this: EM equals EK plus EP. It probably gives you enough information to find this, and I think it outright gives you that. Okay, so I think you can figure out what you got to do to get EP for question number 9. Okay, give you a couple minutes on that one. All right, so number 9, we know the mass is 55 kilograms. Okay, and we know the mechanical energy is 3,000 joules. Okay, and the speed is 8.33 meters per second. All right, so those are our givens. Okay, so I know the total amount of mechanical energy involved. And since I know the mass of the athlete and how fast they're going, I can calculate the kinetic energy of the athlete. So how do I get EP then? Subtract. Right, I subtract this one over to this side. If I know what they add up to is 3,000 joules, and I can find out one of the two, I just bring it over here and solve for the one I was missing. Okay, everyone follow me there? Right, so I'm going to go 3,000 joules, okay, the total mechanical energy, equals, okay, minus the kinetic energy, equals EP. So all I've done is subtract EK from both sides to bring it over here. All right, now I'm going to plug in my formulas. 3,000 joules, okay, minus 1/2 times the mass, which we were told was 55 kilos, multiplied by his speed squared, 8.33 squared, and that's going to equal EP. All right, and when I do that, okay, on my calculator, 3,000 okay, minus 0.5 times 55 times 8.33 squared. Okay, so there's 1,091.8 joules of potential energy as they're going over the bar. Okay, everyone follow me on that one? Okay. As long as I understand that those two things add up to mechanical energy, if I know one of them and I know what they add up to, I can always find the other. All right, so the same idea then goes for question number 10. Okay. This time you're being asked to calculate the kinetic energy of the hammer instead of the potential energy. So give that one a try and we'll go over it in a minute. All right, so for number 10, we know that the mass in number 10 is 2 kilograms. Okay, and the hammer is 50 meters above the earth, and it has a total mechanical energy of 1.88 times 10 to the 3 joules, which is 1,880 joules. We want to calculate the kinetic energy. So mechanical energy equals kinetic plus potential. So if I want to find kinetic, I subtract potential from both sides. So I'm left with this: mechanical energy minus potential energy equals kinetic energy. Okay, then I can plug in my numbers. 1,880 joules minus M, which we said was 2 kilograms, times G, 9.81, times the height, which was 50 meters. Right, and that should leave us, okay, with our kinetic energy being 899 joules. Okay, Everybody with me there? All right, let's take that one step further. What if the question asked, instead of what's the kinetic energy of the hammer, it asked you what's the speed of the hammer? Could we calculate that? Yeah. Okay. Since we know EK and we know M, it would just be a matter of manipulating 1/2 mv squared in order to find V. All right. Now, what that would look like in this equation would be this. Okay. We would go 1/2 mv squared, and now I would bring the half of m over to this side. Agreed? Okay, so I divide both sides by half of m. And then what? And then square root. Okay, now, is this starting to get crazy full of numbers? That's the stumbling block for most people to do these successfully, is that it simply becomes a lot of numbers to enter, which is why it is so important to show your work at every step. Just in case when you get to the calculator part of this, you punch something in wrong. All right? That way I can look at your work and go, oh, well, they clearly knew how to do this. They showed all the right steps, and then obviously got clumsy fingered on their calculator and didn't punch it in right. Then you're getting, like, let's say 6 out of 7 or 7 out of 8 on a question like that, okay, because you showed all your work, and I can clearly tell that you knew how to do it. All right? All right, so let's have a look at this one here. I got an average force of 100 newtons required to pull back a bowstring a distance of 1/2 meter, and the bow is aimed vertically. So just like the example we talked about a minute ago. How much work is done on the bow? What was I given? I was given force and distance. Can I go force times distance to calculate the work? Okay, so 100 multiplied by 0.5 is 50. All right, so there's 50 joules worth of work done on the bow. From here on out, I do not need to do, okay, any math. If I understand the law of conservation of energy, I should have to do no additional math to answer any of the next 3 questions. How much potential energy did I put in the bow? 50. I stretched it, right? I did work. I pulled the bowstring back a distance by exerting a force. That means I put potential energy in the bow. And according to the law of conservation of energy, if I did 50 joules worth of work, there has to be 50 joules worth of energy now in the bow. Everyone follow me there? Okay, so 50 joules. Okay, how much kinetic energy will the arrow have when I release the bow? 50 joules. I can't create energy. I can't destroy it. There's only 50 joules worth of energy in the system. No part of the system can have more or less than that. All right, so 50 joules. How much potential energy will it have when it gets to its highest point? So if we shoot it straight up in the air, when it's at that point there where it stops and turns back around and comes back down, okay, how much potential energy will it have up there? 50 joules. Okay, if we understand that concept, we understand the law of conservation of energy. Okay, I have occasionally put a question like that in as like a multiple choice kind of a thing, okay, on a unit exam. All right, something like that. All right, we already did those. Okay, so the law of conservation of energy works like this, and you've got this page in your booklet there as well. Okay, so the law of conservation of energy states that the total amount of energy in a given situation remains constant. Okay? Energy can be converted from one form to another, but the total amount of energy never changes. Okay? The total amount. So when we're talking about that arrow example, okay, as the arrow travels up into the air, it's losing kinetic because its kinetic is being turned into potential. Okay? And on the way back down, the opposite is true. The potential energy is being turned into kinetic. Okay? This is how a roller coaster works. Okay? The roller coaster is the simplest and most pure example of the law of conservation of energy. All right? In a traditional roller coaster, so I'm excluding roller coasters like the Hulk, okay, where you are shot out of the beginning. Okay? Most roller coasters, you are towed slowly to the top of the first hill. Okay? Is work being done on you at that time? Yeah. Okay? Because it's giving you the mechanical energy potential in this case, but it's giving you the mechanical energy required to complete the ride. Okay? If you've ever looked closely at a roller coaster, the first hill is always the highest one. There's no point on the roller coaster that is as high as the first one. Why? Right. It wouldn't be able to get up that high. Okay? It's towing you to the top of the roller coaster. As you go down, you can't get up any higher than you were at the beginning. Even if it was a perfectly frictionless roller coaster where you didn't lose any energy to sound and heat and all that kind of stuff, it couldn't get back up to that height. Okay, well, it could get, if it was perfectly frictionless, it could get back to that height, but it can't go higher, because if it did, it would have to have work done on it, or it would have to have created energy somewhere along the way. All right, everyone follow me on that one? So the next hill down is always a little lower, okay, and a little bit lower than the next one. Right, and if you've been on the one at Callaway Park, that's kind of the closest one to us, you can see that. Okay, there's one hill that is obviously higher than the others. The loops and everything are all lower, okay, than that first hill. All right. So in a case like this, okay, where we've got the arrow that goes up and then comes back down, its maximum potential energy equals its maximum kinetic energy. Everyone okay with that? Okay? And the reason we say that is because, really, we write the law of conservation of energy like this. The initial energy is equal to the final energy, and these would both be mechanical. Right? My initial mechanical energy has to equal my final mechanical energy. That's the law of conservation of energy written out mathematically. Right? Now, we can expand on that, and we can say this. The potential energy initial plus the kinetic energy initial, is that how we calculate mechanical? Right, we add those two together, equals, okay, the final potential plus the final kinetic. Okay? Now, does the amount of kinetic on this side have to equal the amount of kinetic on that side? It doesn't. Okay? As long as they add up to the same number, we're good. Okay, so no, this kinetic and this kinetic don't have to equal each other, as long as this plus this equals this plus this. And so that's kind of true if we're looking again at that bow and arrow example. Okay, down here at the bottom, the initial kinetic energy was a big number and the potential was 0. But up here at the top of the flight, okay, so over here, the kinetic energy was 0 and the potential energy was that same big number. Right? So as long as they add up to the same number on both sides, we're obeying the law of conservation of energy. Okay. All right. So let's look at this example here. If I have a 1.5 kilogram rock dropped over the edge of a cliff 30 meters above the surface of the lake, what's the speed of the rock just before it strikes the surface of the lake? So I'm gonna cross off what they have here because I don't like what they do here. Okay? Because it's going to lead to mistakes later. Okay? Can I know for sure that if I drop a rock off of a cliff, that the energy it had when I dropped it will be the energy it has when it hits the lake? Yes, I can. Okay? Because the law of conservation of energy tells me so. All right? So that means the initial energy when I dropped it equals the final energy when it strikes the lake. They're not going to be in the same form, because when I dropped it, it only had potential. When it strikes the lake, it's only going to have kinetic. All right, but they're going to be the same number. All right, so I'm going to say, here's my initial mechanical, here's my final mechanical. Okay, so potential initial plus kinetic initial equals final potential plus, okay, final kinetic. So since we're crossing off what they did, write down what I'm doing here. All right, now here again is where context matters. Okay? In the context of this question, we know that because I'm dropping the rock, it has no initial what? It has no initial, what kind? It has no initial kinetic energy because it has no initial speed. All right, anytime something is dropped, its initial speed is 0. All right, so that means that this number here is 0, and as a result, I'm going to get rid of it. Why would I write that extra formula in there to confuse myself if I don't have to? Okay. Similarly, on this side, the end point of this question is the surface of the lake, where the height would be 0. And as a result, this would be 0. All right, so I'm left with that the initial mechanical energy equals the final mechanical energy, yes, but that means the initial potential equals the final kinetic because these two numbers here were 0. So I can now say this. M times G times HI equals 1/2 mvf squared. I know those two numbers are equal. All right, the question wants to know how fast the rock is going when it hits the lake. So it's asking me to solve for VF. How do I get VF by itself? Divide by half of M. Okay, in this situation, can I cancel M? Yes. In this situation, I can cancel M. M is the same on both sides. Okay? And I don't have any other operation up here. So I'm going to save myself a little work. If I plugged M in, it would get me the same answer, and I'll show you that in a minute. Okay? I could leave M in there. If you're not comfortable canceling it, leave it in. It won't make any difference. All right? And now what do I need to do? I need to square root. Okay, so the mass of the rock was what? 1.5 kilograms, and the height was 30 meters. Okay, so when we've got this situation here, I'm just going to transfer over to this side, guys. VF is going to equal the square root of 9.81 times 30 meters, okay, divided by 1/2 square rooted. Okay, and that'll give me the speed of the rock when it strikes the water. All right, so 9.81 times 30 meters, and it gives me that, divided by 1/2, gives me that, square root that. It's going to be moving at 24.3 meters per second when it strikes the lake. Now, we said we could leave M in there and it wouldn't make any difference. Okay, so if you're not comfortable canceling M, I'm going to show you that if I put M in there, it doesn't make any difference. All right, so the mass was 1.5 kilograms. So if I go 1.5 times 9.81 times 30, okay, gives me that. If I divide that by half of M, okay, and then square root that, it's the same number. Okay. 24.3. So if you're not comfortable canceling M, you can plug it in. You can put in the mass in every single operation. It's just more work. Okay, but it'll give you the same answer. All right, is everybody following me there? We're going to be working on that kind of stuff next week, except next week it'll be more, it's got both kinds of energy at the beginning and the end, so there's a little more stuff to move around. It's still just algebra, okay? And that part of it isn't terribly difficult, but okay, there's going to be a lot more algebra stuff to do when we're doing these kind of questions. All right, I want you guys to try question number 11 here before the bell goes. Okay, hopefully we'll have a chance to go through that. So, real simple here, guys. Okay, we started out, and all law of conservation of energy problems start out with this EI equals EF. All right, because that's what the law of conservation of energy is. How do I know the difference between a law of conservation of energy problem and a work energy theorem problem? Okay, it's going to talk about 2 points for sure. Okay, a law of conservation of energy is going to talk about 2 points. It's going to talk about 2 different kinds of energy most likely. Okay, and I will never see the word work in a law of conservation of energy problem, because if work's done, the energy is going to change. In this, the energy is clearly not changing, as the final and the initial are the same number. Okay, so that tells you sort of how to tell them apart. All right, initially, I dropped it, so it only has what kind of energy? All right, we'll finish that on Monday.